everyone, welcome to my YouTube channel Erudispace. I am Dr. D Mohanty, and today we will discuss about the second law of thermodynamics. So before discussing the second law of thermodynamics, first I'll tell you what are the limitations of first law of thermodynamics. Then what is a heat engine, what is a refrigerator, and what is a heat pump, what is thermal energy reservoir. Then we'll discuss the two famous statements of second law of thermodynamics, and then I will prove that both the statements are equivalent in all respect. So first, what I am going to discuss is what are the limitations of first law of thermodynamics. So what is first law of thermodynamics? First law of thermodynamics is a form of law of conservation of energy. According to law of conservation of energy, energy can neither be created nor be destroyed. It can only be converted from one form to another. Joule has conducted the famous paddle wheel experiment in which he found that the work transfer is equal to the heat transfer. That means W has been found to be equal to Q. So that he broadly concluded that work and heat are mutually convertible. Is it 100% right? No. They are convertible, but 100% conversion of work energy to heat energy is possible, but not the other way around. So when work is converted into heat, then this expression holds good, and when heat is converted into work, this expression doesn't hold good. That means the work output that we get is found to be significantly lower than the heat input we provide. But does it violate the law of conservation of energy? No. The heat energy is converted into some other form which we are not in a position to utilize. And work is, that's why, known as high grade energy, and heat is known as low grade energy. 100% conversion of high grade energy to low grade energy is possible, but not the other way around. Then, what are the limitations of the first law of thermodynamics? First law of thermodynamics doesn't give any idea about the directional nature. It cannot tell. Suppose this is not a marker pen, this is a metallic bar, and the temperature is uniform throughout. First law cannot say whether this will automatically become cooler and this will become hotter. What it can tell, that if the process did occur, the heat lost by this end is equal to the heat gained by the other. Spontaneous things always happen in a particular direction. Heat always flows from high temperature body to a low temperature body. Water always flows in downward direction. Time always moves in forward direction. Electricity flows from high potential to low potential. So this driving force is what we call your cause, and what we get is the effect. So it is very, very important to understand that the first law can never tell you that whether the process is practically feasible or not. So after that, I will tell you what is a thermal energy reservoir. Thermal energy reservoirs are energy reservoirs of infinite heat capacity, so that the transfer of heat to the thermal energy reservoir or the transfer of heat from the thermal energy reservoir will not affect its temperature. And this will find extensive application once we discuss the heat engine and heat pump. You can draw an analogy with a particular example. Suppose you consider the amount of water that is present in ocean. Suppose you add 5 liters of water to it, or you withdraw 5 liters of water from it. will it affect its volume? No. Whatever is happening is very, very insignificant in comparison to the total volume of water that is present in the ocean. Even if you enter 50,000 liters also, the same thing. It will hardly affect. The same is about the thermal energy reservoirs. Thermal energy reservoirs are reservoirs of infinite heat capacity, so that the transfer of heat to it or transfer of heat from it will affect its temperature. We will consider the concept of source and sink once we discuss the heat engine. Now, I will tell you what is a heat engine. In heat engine, there is a net heat transfer to the system and net work transfer from the system. So, I will take two typical examples to tell you what we actually mean by heat engine. So, this one is a typical example of heat engine. This is nothing but a piston and cylinder machine with some amount of gas content in it. This is Q1, that is the amount of heat transferred to the gas which is present here, and Q2 is the amount of heat that is delivered from the system. WC is the amount of work that is done, and WT is the amount of WE, not WT. WE is the amount of work we get. So this can be considered to be a heat engine because there is net heat transfer as well as net work transfer. Another is a steam power plant consisting of a boiler, a turbine, a condenser and a pump. This is generating power. This one is a boiler. This is a thermal energy reservoir. You can consider this to be a furnace of infinite heat capacity. Then you have a turbine. This is nothing but an expander, and it is doing WT amount of work, and then that is taken to a condenser. This is another thermal energy reservoir of infinite heat capacity. You may consider this to be your atmosphere. This is the turbine. This is the condenser. It is liberating Q2 amount of heat to the atmosphere, and then you have a pump. And here WP amount of work is done for the system, and here of course is H2O. This becomes your H2O vapor. The phase changes are taking place, but it is water all along. Water or steam when it moves from boiler to turbine to the condenser and the pump. From the boiler, actually it receives heat. After that it is taken to the turbine where it does WT amount of work. Then it comes back to the condenser where it liberates heat to the surrounding condensing medium. Q2 is the amount of heat that is delivered to the surrounding condensing medium, and then the pump is actually pumping the water back to the boiler to start new cycle, and this is the amount of work that is done. So in both the cases, the amount of heat transfer is equal to amount of net heat transfer is equal to net work transfer. So you have Q net is equal to W net, or summation of Q is equal to summation of W. So if you consider this one, then Q1 minus Q2 is equal to your WE minus WC, and the net heat supplied is equal to Q1 minus Q2 in both the cases. In case of the piston cylinder system as well as this power plant. Now, if you consider this one, Q1 minus Q2 is equal to WT minus WP. You can consider the total amount of work or the net work, as I have already told you, W net is equal to WT minus WP. And the performance parameter of the heat engine is what we call its efficiency, eta. What is efficiency? It is the net work output divided by the heat supplied, that is W net divided by heat supplied. So this is all about the heat engine, and this is something you can show in a very simplified diagram. So let me draw the simplified diagram, because mostly we will use the simplified diagram when it comes to the analysis of the second law of thermodynamics. So diagram, again we will have one source, one sink, then this is maintained at T1, this is maintained at T2. So here you do have a boiler here, then you have the turbine, then you have the condenser, then you have the pump. The same things are there, but this one is much simplified, and it may be represented as W net, which is nothing but WT minus WP, and this will be primarily be used. In this case, the efficiency will again be the net work that we do, that is WT minus, this one is actually WP, divided by heat supplied. So now I will actually discuss about the refrigerator and heat pump. First, about the refrigerator. The refrigerator is something that maintains a body or a space at a temperature lower than the atmospheric temperature. So here also you are having two thermal heat reservoirs, and then this one is your evaporator, then you have a compressor, then it is taken to a condenser, and then it is taken to an expander, and we use a suitable working substance which is called your refrigerant. This is maintained at temperature T1 and this is maintained at temperature T2, and T1 is greater than T2. Now this one is your evaporator, this one is your compressor, this one is your condenser, and this one is your expander. The direction of flow of the refrigerant is in this direction. So first the liquid refrigerant will enter the evaporator and it will receive the latent heat of evaporation from the medium to be cold, then will be evaporated, and then this is taken to the compressor. In the compressor it is compressed, and then it is taken to the condenser. In the condenser it will liberate heat to the surrounding condensing medium. So this one is Q2, that is the heat that is extracted from the space to be cooled, and this is Q1, this is the heat that is to be delivered to the surrounding condensing medium, and here WC amount of work is done, and here we get a work output of WE. So W net is equal to WC minus WE, that is the work that is spent in the compression minus the work that is obtained in the expander, and that is equal to Q1 minus Q2, because the net heat transfer is equal to the net work transfer. Now, what is the performance parameter of the refrigerator? The performance parameter of the refrigerator is known as its coefficient of performance, abbreviated as COP. So what is COP? COP is equal to desired effect divided by heat input. So what is desired effect? Desired effect is WC minus WE, and what is the heat input? Sorry,
pause.
Now the COP is the desired effect divided by the work input. So what is desired effect? Desired effect is extraction of Q2 amount of heat from this reservoir, so that it is maintained at low temperature. So what is work input? That is WC minus WE, that is the work that is spent in the compression minus the work that is obtained in the expander, that is Q2 divided by Q1 minus Q2. What about the heat pump? As far as the cycle of operation is concerned, there is no difference between the refrigerator and the heat pump. Only is the objective. In case of refrigerator, our objective is to maintain a body at a temperature lower than the atmospheric temperature, whereas in case of a heat pump, the objective is to maintain a body at a temperature higher than the atmospheric temperature. So that is the only difference that exists between the refrigerator and the heat pump. The performance parameter of the heat pump is known as the energy performance ratio, or EPR. Some people do use the term COP of heat pump as its performance parameter, but the usual performance parameter is your energy performance ratio. Again, this is the ratio between desired effect divided by the work input. So what is the desired effect? In this case, desired effect is delivery of Q1 amount of heat to this reservoir so that it is maintained at high temperature, divided by work input. Work input is again the difference between the work that is spent in the compression minus the work that is obtained in the expander. This is Q1 divided by Q1 minus Q2, and this is nothing but COP of the refrigerator plus 1. So this is all about the operation and functioning of the refrigerator and the heat pump. I will take a separate lecture to discuss about the refrigerator, heat pump as well as the heat engine. So now this is the simplified diagram of the heat pump. You have all the components. You do have the evaporator, you do have the compressor, you do have the condenser, you do have the expander. Here we are using the notation E1 and E2 for evaporator and expander because both the evaporator as well as the expander, they are starting with letter E, and similarly we are using C1 and C2 because both the compressor and condenser are starting with letter C. This is important because when it comes to the analysis, we will only consider this as a single entity. Actually, even those components will not be shown. It will be just like this. This is the way the heat pump is to be represented. Already we have discussed that how the heat engine works. So here also the parts like boiler, then turbine, then condenser and pump will not be shown. It will be just shown in this way. These are very, very important for all of us to know before making a comparison between the two statements of second law of thermodynamics. As far as the operation and the functioning of the heat engine as well as heat pump are concerned, I have explained everything in details. But what I have not explained, why the heat is flowing, why heat is being absorbed or why heat is being delivered, what is the driving force behind this, that we'll discuss once I completely explain the second law of thermodynamics, and I have kept a separate lecture to discuss the operation of the heat engine, heat pump as well as refrigerator. So after giving you a brief idea about the limitations of first law of thermodynamics, the thermal energy reservoirs, heat engine, refrigerator and heat pump, I'll tell you what we actually mean by second law of thermodynamics. The second law of thermodynamics is different from other laws because so many people have worked to develop the second law of thermodynamics. And there are two popular statements related to the second law of thermodynamics. The first one is given by Clausius and the second one is given by two scientists, Kelvin and Planck. So what is Clausius' statement of second law of thermodynamics? According to Clausius, it is impossible to construct a device which, while operating in a cycle, spontaneously transfers heat from a low temperature body to a high temperature body. So spontaneously heat can never flow from a low temperature body to a high temperature body. That's what actually Clausius meant. And then the second statement is given by Kelvin-Planck, and according to Kelvin-Planck, it is impossible to construct a heat engine which will produce net work in a cycle, exchanging heat with bodies at a single fixed temperature. So when you consider both the statements, at the first sight they appear to be quite different, but they are actually two parallel statements of second law of thermodynamics, and we will actually prove that both the statements are equivalent. So we can prove that if we can prove that the violation of the Clausius statement violates the Kelvin-Planck statement and violation of the Kelvin-Planck statement violates the Clausius statement. Now I have considered two specific examples. First one is violation of Clausius statement, and here I will prove that violation of the Clausius statement also violates the Kelvin-Planck statement. The second one is violation of Kelvin-Planck statement. I will again prove that the violation of Kelvin-Planck statement violates the Clausius statement. So here let us consider a heat pump that is transferring heat from a low temperature body to a high temperature body spontaneously. That means with consumption of zero amount of work, it is transferring heat from a low temperature body to a high temperature body. You should remember that T1 is greater than T2. Now, we have to prove that it also violates the Kelvin-Planck statement. Let us imagine a heat engine which is operating between the same temperature limits T1 and T2, and it is requiring exactly the same amount of heat that is being delivered by the heat pump to the high temperature reservoir. If this happens, then the heat that is being delivered to the high temperature reservoir may be directly delivered to the heat engine. Now, this heat pump and heat engine put together form a heat engine which is producing net work by interacting with a single heat reservoir, because if it requires the same amount of heat as being delivered by the heat pump, this heat reservoir may be eliminated. So we have successfully proved that the violation of the Clausius statement also violates the Kelvin-Planck statement. And this is the second example where I have considered the violation of Kelvin-Planck statement. Let us consider a heat engine which is producing net work, exchanging heat with bodies at a single fixed temperature. It is extracting heat from this reservoir maintained at temperature T1 and converting the entire amount of heat into work. Now, let us consider a heat pump which is operating between two temperatures, T1 and T2. And the amount of work input required to operate the heat pump is exactly same that has been delivered by the heat engine. Now, it is extracting Q2 amount of heat from the reservoir that is maintained at T2, and it is delivering Q1 plus Q2 amount of heat to this reservoir. Now, this heat engine and heat pump put together form a heat pump which is spontaneously extracting heat from the low temperature reservoir and transferring it to the high temperature reservoir, thereby violating the Clausius statement, because these two units has now become a single unit, which is your heat pump, and it is spontaneously transferring heat from the low temperature reservoir to high temperature reservoir. So now we have successfully proved that both the statements are exact and equivalent in all respect, and they represent the second law of thermodynamics. Although the lecture was a bit longer than the usual lectures, but I sincerely believe that after watching this video, your concept about the second law of thermodynamics, the reason for developing the second law of thermodynamics, the limitations of first law of thermodynamics will be crystal clear. If you have any doubt, please do put questions so that I will try to answer those questions. Thank you for watching this video. Hope to see you soon for another lecture for my YouTube channel, Erudispace.